Hi, my name is Talia. I'm a high school senior and I love teaching others about chemistry and math. This YouTube channel is a supplemental resource to anyone who may be having difficulty in their chemistry classes and wants an extra boost of knowledge. This week, I'm going to be talking about balancing reactions algebraically. This is a new way to balance reactions when they might be a little bit different than the traditional kinds of reactions I've discussed in previous videos. So if you would like to learn more about balancing algebraically or just need some help with the topic, feel free to keep on watching. Without further ado, let's get started.
So you can basically assign variables to each of the compounds in a reaction, and then you'll make equations and be able to use the variables to get the coefficients in front of each compound. So I'm just going to follow this set of steps. I'm going to first write a coefficient for each chemical in the reaction as a letter. So I'm just going to go down the line. So our reaction is SN plus H2O4 yields SnSO4 plus H2O plus SO2. So you might also be asked to balance algebraically when you have a lot of compounds being used and they don't necessarily fit into one of our traditional reaction types that I showed you. Like for instance, a double replacement is two elements, is two reactants, two products. This is two reactants, three products. So it's a little bit different. So now I'm going to write an equation for each element in the reaction using the number of atoms of the element on both sides of the equation. And I'm going to separate polyatomic ions in this case. So this basically means that I'm going to use the variable on the reactant side and set it equal to the variable on the product side. And I will multiply the variable depending on how many subscripts of the element there are. So this will make more sense once we continue on. So I have one A on the reactant side because I have one SN. So A equals C because there's one SN on the product side. Now I'm going to do hydrogen. I have two hydrogens on the reactant side, so I'm going to write 2B because I'm going to multiply B by the amount of subscripts for the element. And then on the right side, we have 2D. Now I'm going to do sulfur. I have B equals C plus E because there's sulfur in two locations. And finally, I have oxygen. 4B equals 4C plus D plus 2E. Okay, so now what I'm going to do is the next step, set one of the variables equal to 1 and then use that to solve for the other variables. However, before I do that, I'm going to see if I can simplify any of my equations just because it will make it a little bit easier to solve for the variables. So I can simplify my hydrogen equation and just write B equals D. So for the step with setting one of the variables equal to 1, you have to be really careful and make sure that you don't set a variable equal to 1 that is not going to get you anything else. So for instance, if I set E equal to 1, that wouldn't really help me because I have other variables in the equation and it would just be really complicated. So I'm going to let A equal 1 for this problem. And you'll get better at figuring out which variable to set equal to 1 as you have more practice. So now I'm going to solve for all the other variables. So if I have A equals C, then that means C also equals 1. So now I figured out the coefficient in front of SnSO4. So next I would maybe think to go to the S equation for B equals C plus E, but I don't have B and I don't have E. And however, I have an equation that says B equals D, and I have an equation that incorporates all three of those variables, all four of those variables. So I'm going to do some substitution and use my equation that says B equals D in order to get rid of the D variable in the fourth equation. So I'm going to write out 4B equals 4C plus D plus 2E. So now I'm going to substitute what I have. 4B equals 4. We know that C is 1. And we know that B equals D. So we have plus B plus 2E. Now I'm going to simplify. So I have 3B equals 4 plus 2E. now we have this equation, and we now will ping pong back over to one of our original equations because we can see that B equals C plus E. So here's another instance of where we can get rid of one of our variables. We can get rid of our B and make the whole equation in terms of E, which will simplify further. So I'm going to use my solve for equation and write 3 times C plus E equals 4 plus 2E. So now I have 3 times 1 plus E equals 4 plus 2E, and that is going to simplify. And now if I solve for E, I get that E equals 1. So to quickly go over what I did, because that was a lot of steps. I could not immediately use the solve for equation because I didn't know B or E. So I used the equation that had B, C, D, and E combined because I also have an equation that says B equals D. So I knew I could substitute. So I wrote the original equation and then I substituted B for D. So I have everything in terms of B and E, but I encounter that problem one more time where I have 2 variables. So I do substitution again. I have an equation that says B equals C plus E. So I plug in C plus E where B is. And then I plug in everything I know, and I'm able to solve for one variable. So now I have E. So now let's get B, because in the solve for equation, we have C and E, so we can get B. So B equals C plus E, which means B equals 1 plus 1, which means B equals 2. And now our final variable we need to get is D. So I'm going to just set B equal to D, which means D equals 2. So now we have solved for all of our variables. And I'm going to rewrite my equation. I'm going to try to fit it down here. So now that we've solved for the variables, we know what all of our coefficients are going to be in the reaction, and we didn't need to do the chart because it would have been very complicated that way. So I'm going to rewrite my reaction as Sn plus, and then what is B equals 2, so 2H2SO4 yields SnSO4 plus 2H2O plus O plus SO2. Now, if you wanted, you can check to make sure it's consistent with the law of conservation of mass. We have one Sn on both sides. We have 4 hydrogens, 2 sulfurs, and 8 oxygens. So this method will work for simpler equations as well. I just think for simpler ones, it's easier to use the chart, and for more complicated reactions, it's easier to balance algebraically. Just a note that was not in this problem, but might end up in one of your other problems when you're balancing algebraically. You might end up with a fraction of a coefficient that is equal to a variable, like if D was equal to 1/2. And in a response to that, you just multiply the coefficients by the same number. So like, let's say you had D is equal to 1/2, you would multiply all of the coefficients by 2. So that is how you balance algebraically. It does take some time to fully get into the practice of it and immediately know which variables to make equal to 1. But as you do it more and more, if you are even required to do it by your teacher, you will understand it better, and hopefully it will be a super convenient trick you can use when balancing with a chart does not help you.
I hope you enjoyed this week's video. Next week, I'm going to be starting a new unit on stoichiometry, and I'm going to begin by talking about mole conversions and basic mass to mass stoichiometry. Feel free to join me back next week for that video if you would like some help with those topics. Also, if you have any questions, go ahead and leave them in the comments and I will do my best to answer them. I will also leave a link in the description box to my website if you would like to schedule tutoring with me. I hope you enjoyed this week's video, and good luck with learning the rest of your chemistry.